Are we ready to start?
Estamos listos para iniciar, está grabando.
Sí, estamos listos, Roberto. We're ready.
Okay, so I'm going to introduce Jim, right?
Yes.
Okay, well, welcome. Bienvenidos todos al seminario del Centro de Geociencias que presenta hoy Jim Pindell, que está ahí en la pantalla. Jim se graduó de la Universidad de Durham en el 85. Jim es un caso muy especial entre los científicos porque después de terminar el doctorado, en lugar de seguir la ruta tradicional que es trabajar en alguna universidad, Jim empezó una empresa consultora, Tectonic Analysis, que ofrece el servicio de ligar la tectónica de placas a la evolución geológica para la prospección, para la exploración de petróleo. Aún así, Jim es un científico muy productivo que ha trabajado principalmente en el Golfo de México, el Caribe, el margen andino de Sudamérica y más recientemente junto con un consorcio que se llama ION, ha trabajado mucho en márgenes pasivos. Jim tiene más de 80 artículos muy citados, más de 4,000 citas, dice Scopus, y se le considera, pues sí, uno de los geocientíficos más influyentes con lo que respecta a la geología del Golfo de México y del Caribe. Entonces, Jim, do you want to put your title slide in the screen? And el título de la plática es ahora lo voy a decir de memoria porque no lo tengo en la pantalla, pero es como la evolución de la sal, los datos aeromagnéticos, la topografía dinámica y el movimiento absoluto de placas con respecto a cómo influyeron en la apertura del Golfo de México. ¿Ya? Entonces, sin más que decir, ahí está Jim con ustedes. Jim?
Yes.
We're ready to start.
My screen should be showing. I think
it is showing. Yes, it is showing in
okay.
Not full screen on my computer. It's showing with the thumbnails.
Really? Okay. Let me stop sharing. I'll go back to this. And now I will try that again. Full screen mode. How's that? Is that better?
You're not sharing yet.
Okay, I see. All right. Recording, leave, share screen. Okay. Can you see that again now?
Yes.
Now I go to full screen. Yeah?
Okay. Well, we still see the thumbnails, but I think you can just close that page thumbnails panel.
Yeah. Okay, I'll do it the other way. I'll just grow this.
Yes, that's
yeah.
Perfect.
Is that good enough?
That's good enough. Thank you.
That's weird. Okay, I thought that usually worked. Right. Well, thank you, Roberto, and thank you, Uwe, for inviting me to speak as part of your program this summer. When Roberto asked me to speak about 3 months ago, I was working on something to do with dynamic topography and absolute plate motions. And those things do play a role in the Gulf of Mexico. And I was excited about it and I wanted to talk about it. But as I started to prepare this talk, I decided I should probably focus more on what we've done in the Cordilleran program for the last 10 years, which has involved the collaboration between myself and other colleagues and UNAM Querétaro. So that's what I'm going to do. We could give it a better title, Synthesis of the Opening of the Gulf of Mexico, perhaps. First, I want to thank UNAM and UNAM Querétaro directors Luca Ferrari, Gerardo Carrasco, and Lucia Capra for collaborating with the Tectonic Analysis program in the Cordilleran Research Program. I have had a lot of fun and rewarding experiences in this, and I hope it's a two-way street. We've gotten quite a lot done. I think we have about 34 papers published in peer-reviewed journals, and there are several more still planned to come out. I want to thank all these people you can see here. I don't want to read all their names, but they have played critical roles in the program, especially Roberto, Uwe, Rod Graham, Maria, and Diego. And we'll talk about some of the work that other people have done as well. I'm indebted to Pemex, CNH, Petrotrin, and ION for data provision, cores, seismic, so on and so forth. That has allowed the integration of the onshore and the offshore much more effectively. And of course, the funding for all of this has come from a bunch of oil companies. This is the way I have operated going back to about 1985. We have worked on the Andes, we worked in Colombia, we worked in Venezuela, we worked in Trinidad, and the last 10 years we've been working in Mexico. And I don't know what's next. Here's 17 of the papers that we've published and their authors. I don't know if you can see that. And here's the other 17. So we're up to about 34 published papers. And there's one good thing about COVID and the lockdown, and it's forced us to publish papers, and probably 20 out of the 34 will be published in the years 2020 and 2021. And that's because everything else was put on hold and we had nothing else to do other than to finish our papers. As introduction to the region, I don't know how much time I need to spend on this, but I'll just start from east and head west toward Mexico. We can see the Atlantic magnetic anomalies, which control the opening of the Atlantic and therefore the relative plate motion framework for understanding the Gulf of Mexico and Mexico. The Blake Plateau and the western part of the Bahamas, what we call the Great Bank, is underlain by continental crust. The eastern part of the Bahamas is probably a hotspot track. It's perfectly parallel to the fracture zones, as you can see, so that makes sense. In western Florida, there is an array of horse and graben, which are very significant, and they were formed at a crustal scale and probably represent a lot of intercrustal extension. And we need to account for that in any model of opening in the Gulf of Mexico. Out in the middle of the Gulf, I hope you can see my hand, my pointer. There's the outline and dashed line of the area of oceanic crust. We have mapped that at ION geophysical pretty accurately, I think. So out in the middle of that area is ocean crust, and there's ocean crust that formed by spreading around two different poles of rotation. You can see that in the two different colors. The outer one was formed by one pole of rotation, and then the central darker color is formed around another pole of rotation. It's not that critical to the story, but it is something we've learned in the last several years. The interior salt basins lie up here to the north. These are all onshore and very much over thick continental crust. And then there is a series of highs, the Wiggins Arch and the Angelina Caldwell flexure. These form sort of a step in the basement. And from there, we head down into the deeper Gulf of Mexico, and we get into very thick sedimentary sections in the Gulf Coast off in this area here. There are two magnetic anomalies, the Houston magnetic anomaly in the coastal zone of Texas, and also the Campeche magnetic anomaly in the northern part of the Campeche Basin and through here. And when we reconstruct the Gulf of Mexico, these two anomalies end up lying on top of each other, and that might be telling. It might help understand what those are. Perhaps it was a single basalt-laden rift at the time of Rift extension, something like that. As we go into Mexico, first of all, we can see the East Mexico transform along the east here, and I'll show you some seismic lines across that. It's a very sharp margin, which can only be formed by strike-slip motion. And then we get up into the onshore. The main things to point out are the basement highs, which are highlighted in yellow, and then some of the carbonate platforms in light blue. And in places like Coahuila, these two things interfere with each other. But it's the basement highs which appear to be separated by northwest, southeast trending fault zones, which I'm going to be talking a fair amount about, because they offer us the possibility of a new means of getting the continental crust into the overlap position that was once occupied by Colombia, as an alternative to employing big strike slip motion on the Mojave Sonora megashear. So it's a new hypothesis. It needs a lot more work. And right now it's just sitting on the table for people to do with what they want. Farther to the west in Mexico is the area of the Guerrero superterrane, and presumably everything west of that, except for maybe a few crustal slivers, will be comprised of oceanic crust with island arcs sitting on top of them. So the area of continental crust in eastern Mexico is not anywhere near as large as we once thought. And Oaxaca and Acatlan sit down and through here. But you can see a lot of these faults, the Extensional faults across the Tamaulipas Arch. Then we have Huayacocatla, we have Valle Nacional, we have Via Alta, we have the Juarez Mylonites. All of these things generally trend northwest, southeast, and I think that's significant. Okay, I think I'll move on from there. We have understood grossly the evolution of the GOM for a long time. There's two primary phases of opening. There's the drift phase, and to restore that backwards in time, we need to close the oceanic crust. That gives us a reconstruction that looks something like this. For about 40 years, we have thought that that was a lower Oxfordian reconstruction. I think we might want to adjust that now, as I'll tell you. And then prior to the spreading, we have the Rift extension across all the Rift basins, sometimes strike slip faults in playing a role in that as well. And when we close all those down, we come to a full closure reconstruction. And so we can call the Rift the stage 1 and the drift the stage 2. And to close it all down, we have to try to assess the amount of crustal extension that has taken place along these margins and within Florida and possibly within Mexico. And the way to do that is to try to come up with a cross section of what the crust looks like. And then you need to try to shorten that. You have to undo the extension and push the crust back to form an original orthogonal shape of unstretched continental crust. And from that, you can measure the amount of extension, which has grossly gone into the formation of the rifted margins. And so we have to do that to come up with this kind of a reconstruction. And I'll be showing you how to do this when it comes to Florida in this talk. Okay, what have we learned in the last 10 years? First of all, satellite gravity shows us where the spreading ridge in the GOM died. And also the aeromagnetic map, which was provided to us by Pemex, tends to help show more about the spreading history in the GOM. So we'll look at that briefly. We have been able to date salt samples from cores, which have been given to us by Pemex and CNH. And we've dated those with Bodo Weber out in Ensenada, and those turn out to be mostly Bajocian. There are a few ages that were determined back in the 70s and 80s in the interior salt basins, which come as young as Bethonian. But this is about 9 million years older than we ever suspected before. So this requires a fundamental change in at least the age of the reconstructions, if not some of the geometries within them. We've also had another look at the equatorial Atlantic fit, and it turns out that this is probably the most important control on what kinds of tectonic processes are involved in the formation of Mexico as South America pulls away. So we'll look at that. And then there's the Quicoteco belt. To make a long story short, let me just say here that the Heltopotongo-Chavillas Basin, we believe it was opened by sinistral transtension back in the early Cretaceous. And then something that's a little bit more speculative, we think we have pre-depositional exhumation of late Permian and Triassic anatectic granites right to the surface and prior to any deposition of Mesozoic red beds, salt, or marine sections. So we want to ask this question, is this an indication of strong syn-rift crustal extension? And then finally, the crustal extension in Western Florida. This is a more significant number than people think, and I think any attempt to understand the evolution of the GOM must also deal with that extension. Everybody knows this map, and you can see in the dark shades the former outline of the spreading system. And you can see transforms, which are curvilinear, and you can see the ridge segments. And it's almost textbook in terms of how it looks. And if you wanted to play the orthogonal game with the ridge segments and the parallel game with the transforms, or vice versa, sorry, the polar rotation would find itself somewhere over here south of Cuba. But that's literally the only thing that this map really helps us with. It's the death of the ridge at the end of spreading in the GOM. More helpful, I think, is the Pemex Aeromagnetic Map. And you can see, well, there's two main things I want to show here. First of all, the black is superimposed from the gravity onto the magnetics, and that is apparently where the spreading ridge died. So that marks the end of spreading. But then we can see two trends of magnetic anomalies with orthogonal shapes, both in the north and another one down here in the south. And those, we think, mark the ocean continent transitions from the Yucatan and North American blocks onto the oceanic crust of the central Gulf of Mexico. You can see that the blue magnetic anomalies point at one pole and the black magnetic anomaly point at the other one that I mentioned a minute ago. This tells us that there has been a pole jump or a ridge reorganization during the time of spreading. And we can see that especially clear right here. These transforms, these linears here that you can see in the magnetics are not parallel to these ones up here, which you can see in the magnetics. And that's the telltale sign that the ridge has reorganized itself sometime right in through there and right in through there or right in through there. We don't know exactly when that is because none of these anomalies are dated. So this slide shows just what those outer magnetic anomalies appear to be. When we compare seismic lines to the magnetic anomalies, both north and south, it turns out that the magnetic anomalies are marking the edge of the oceanic crust, or possibly the oceanic continental transition. That's true for both the north and in the south. This is a line from Miranda back in 2011. This was his master's thesis. And the southern magnetic anomaly corresponds to the edge of the crust there. And this is not just a GOM thing. This is a global thing. This is the anomaly S1 off of Morocco. This is the coastline of Morocco here. And the S1 magnetic anomaly, which you can see highlighted in blue, is the one that everyone has always used to reconstruct Africa back to North America. And you can see again that it sits in the same structural position as the seismic lines are indicating in the Gulf of Mexico. And basically what it is syn-rift continental blocks stretching toward the ocean. And then there is a detachment system that lets the upper mantle rise to the surface, and its intrusion into that upper mantle, which seems to be responsible for the onset of seafloor spreading. So the possibilities for what makes that anomaly are that it's an edge effect. You get a magnetic anomaly above an edge effect that might look like that. It could be metasomatic magnetite from the hydration of olivine, might look something like that. Or it could just have something to do with that step in the basement shape, as we saw there and there and there. Anyway, that question remains open, and perhaps somebody would like to do some more detailed modeling on that to see if they could come up with an explanation. More at a larger scale of the margins in the offshore, we can see rifted continental crust. This is off of Florida, By the way, I don't show a location map here, but these bright reflectors here are thought by most people to be evidence of magmatic introduction into the syn rift sections above the rifted continental crust. And then you can see this rising mantle surface coming up. It ties into the continental moho back in through here, but it comes to the surface, and that lets the mantle out from underneath the continental crust as it's thinning. And then when that starts to get intruded by oceanic materials, once it gets to be 70, 80, 90% new material, we would want to call that oceanic crust. And this is the structure that seems to form. And you can draw cartoons that look something like this. On the Yucatan side, we see a very similar situation. We have rifted continental crust. We have rotated fault blocks. And in both of these examples, you might be surprised that the main rift faults dip back toward the land instead of down toward the ocean. And this was something that we realized at ION back about 2011 and 2012, and it's made a big difference to the interpretation of rifted margins. This seems to be the most common form of rifting where you have a magmatic type of syn rift deformation. And why that is, I don't know. Nobody's come up with a great explanation for that. But as I said, one course of research may be to consider that the mantle is pulling itself out from underneath the thinning continental crust. And therefore, this kind of a shear system is already set up, because the very basal one down through here needs to be a normal detachment. And it might not be surprising that all these other faults follow the same dip. Anyway, above that, we have syn rift loaded with volcanics, again, from all these bright reflectors. Believe it or not, there are people who know these things, obviously. They think it's obvious. I'm still trying to learn. And then we have the sag section with no faulting above that. And then comes the base salt unconformity. There's not very much salt where this line crosses northern Yucatan. And then we have the Mesozoic section, and the TK is the top Cretaceous, and then the rest of the Cenozoic is there. And this is back toward Campeche platform. Anyway, so similar types of deformation. Here's the oceanic crust, and the detachment comes out through here. So this yellow would be exhuming mantle, but then it starts to get intruded by oceanic crust. And when that starts to happen, we have the formation of oceanic crust. Okay. So this line lets me perhaps convince you that the syn rift breakup in the Gulf of Mexico was more magmatic than other lines tend to show. These are really nicely developed SDRs. This is somewhere off of northwest Campeche, maybe 100 kilometers north of the Tabasco coastline. These are textbook SDRs, and these are thought to be subaerial volcanic lava flows, which came from a source in the down dip direction. So these you can see how these offlap back up toward land. And that's because the flow direction is back toward land. And there used to be a huge volcanic center here, a super volcano. And the flows used to go back toward land. And when that volcano turned itself off, it subsided, and the whole margin rotates from once dipping back toward land, and it subsides so much that these SDRs end up dipping back toward the ocean from the direction that the flows actually came. But that's what these are. And there's the sag section above, there's the salt sitting on top of the sag section, and then the salt is deforming the Mesozoic and the Cenozoic section. And you can see that in Campeche, the salt deformation is active today. It's actually causing bathymetry on the seafloor. When we go over to the Western Gulf of Mexico, we see all of these lines from the ION map that you can see in this yellow oval show a very similar structural style as you see here. We see the oceanic crust coming right up to a position only 20 or 30 kilometers off of full thickness continental crust. So it's a very sharp margin, unlike the other northern and southern sides. We can see railroad type of reflections coming and then onlapping this margin. And you might think, if you cut off the bottom half of this, you might think, well, that looks like a rifted margin. But what's special about this is you can see the continental moho down here very clearly. I've drawn the black line right through those. And that's telling us that the continental moho is 27 kilometers, well, the crust is 27 kilometers thick here. So it's not very rifted at all. It does happen to be pulled down toward the ocean. So let's think about why that might be. And also the time that this section is onlapped. You can see that it takes all the way to the top Cretaceous to be onlapped all the way up to there. So what's going on here is that there is thermal and load subsidence that takes place on the oceanic crust. And as both of those things operate on a long term, it tends to pull the continental crust down with it because this zone is locked. There's no further faulting of a younger age above that juxtaposition between the two types of crust. And the reason for that is because the mantle beneath it it's coupled. You know, there might have been some thinning under the continental crust here, and there's new mantle forming under the oceanic crust. But after just a few tens of millions of years, the upper mantle of the plate is continuous across there, and it doesn't break again. So any load that's applied to the oceanic crust tends to drag the continent down with the oceanic crust. So we can backstrip this very crudely. We know that the spreading in the Gulf is upper Jurassic, so let's call it 144. And the thermal subsidence equation is the square root of T over 3, where T is the age. So if T is 144, the square root of T is 12, and then 12 over 3 is 4. So we have had 4 kilometers of thermal subsidence, and then there's the load subsidence from all the sediment that you can see. And 2/3 of that sediment will depress the oceanic crust beneath it. And 1/3 will be represented by paleobathymetric shallowing. So if we add 2/3 of whatever the sedimentary thickness here is, about 12, I believe, then we have another 7 kilometers of subsidence due to sedimentary loading. So we can add 4 to the 11, and we pull this surface back up from the 12 or 13 that it is, pull it up by 11 kilometers, and we're left with the original late Jurassic crustal configuration that looks something like this in the lower cross section. Okay, where the water is still 2 or 3 kilometers deep, the oceanic crust is 5 or 6, 7 kilometers thick. It's normal, and then a very steep margin. That's the transform margin that we can see with the continental crust. All of these lines show the same thing, so it's very clear where the transform lies. It's offshore until you reach the Trans-Mexican Volcanic Belt, and then it goes onshore into Veracruz Basin. From the Veracruz Basin, we think we can chase it to the western side of Mixtequita Massif, where Roberto has named it the Petapa Fault. And we think we actually found an outcrop with the right types of rock, the expected type of rock we would find here. But so far, we haven't come up with any Jurassic ages, which might date the time of deformation along it. So we're not completely certain about that yet. And then as you chase that into southern Tehuantepec, then that boundary probably becomes overthrust by the Chontal Clip, and we are not able to chase it any further. Okay, what's very interesting about all of this, the southern magnetic anomaly and the northern magnetic anomaly, both of which are shown in black, form very close conjugates to each other. In other words, it's possible to find a pole of rotation where you can rotate Yucatan and the southern anomaly around it, and you can find a pole that lets you plot the southern magnetic anomaly very closely to the northern magnetic anomaly. In addition, we have to keep the western transform sort of collinear upon itself, because we can't let that drift off where it had started earlier in time. And the pole that satisfies this sits on the west coast of Cuba, and you know, way back in 2001, we used pretty much the same exact pole. So enough was known then to get most of the way here, but now this is truly quantitative, and Nguyen and Mann have come up with the same pole. All right, then there's the salt question. We went around and tried to date all the salts related to the breakup between North America and South America. We did the Hockley, we did Mataspino well in Veracruz. We got the Bacab 21 well in Campeche. We went to Trinidad. Those are all the new data. There are salts also in the southern Bahamas, now caught up in the suture belt with Cuba. There's one in Bogota. We dated this one, but it was contaminated and we didn't get a good age for that. And then there's several dozen ages from the interior of salt basins up here, which also, and the long and the short of it is all of the strontium ages for these salt sections turn out to be about 169, 168, 167. Which is very interesting. This is done by measuring the strontium ratio and strontium values and then computing the ratio. And then you can take the long-term strontium ratio history through time. And there's one for the Paleozoic, right through the Mesozoic and into the Cenozoic. This is the Jurassic portion of interest. And all of our data fall in this number, these numbers here. And you can just put your point there and you can go straight down to see what the apparent age is. This method assumes that there is open connection between the world's ocean and the evaporitic section being dated. And I think you can see that there's a close enough clustering here that must have been the case. Otherwise, this data would be all over the place. But Veracruz, this gives a 169. Hockley gave a 169. And there's what's the third one here? And Bacab 21 in Campeche all gave 169. Then we have two 166s. One was from Trinidad and one was a gypsum from the Veracruz Basin. We don't know why we have a halite and a gypsum that gives 3 different years, millions of years, but maybe the evaporitic system was just that long-lived in this epicontinental position up on the continental crust of Mexico, as opposed to the deep Gulf. So this is the time of evaporitic deposition, and now we have much greater control on their actual ages, and we can use those ages and build them into our models. So we know that the salt now is most likely 169, 168, maybe 167. So it's close to Bajocian, Bathonian boundary. We used to think this was early Oxfordian. Now we consider it about 168. So there's about 8 or 9 million years difference. Now that leads to a problem, because when we consider the motions of North America and South America, that 8 or 9 million years brings South America too close in order for Yucatan to sit in this position. Therefore, this reconstruction seems to be too loose for the former 168 reconstruction. So I wanted to check into this as part of the program. And the way this is done, the way we build that relative motion vector between North America and South America so that we know where the two plates were through time. First, we have to close South America back over to Africa. And then we have to rotate Africa, South America back toward North America. That's how it's done. It's a 3-plate process, and we can't try to assess the problem directly from North America to South America because the Caribbean plate is moving, and none of this crust in through here has anything to do with the separation history between North and South America. So we have to go through Africa. It introduces a little bit more error. We might be able to make these reconstructions to 20 or 25 kilometers accuracy. And when you go through the 3-plate reconstruction, you might end up with about a 50-kilometer accuracy when we get to the other side. Here's the old relative motion vector that we have been using for a long time, since 2006, okay? This 68 is much too tight to make room for that new position of Yucatan at 168. So we need to look into this. The two ways of testing this, first of all, we can look at the opening of the Central Atlantic, and we can also look in the reconstruction between Brazil and Africa. When we try to compare some of the more recent efforts to open the Atlantic, we find very close agreement. I think my data was the black line and or dots, and a paper by Exxon, by Neller et al. 2012 with red dots. And you can see that these are perfectly compatible with each other. We use slightly different numbers, but still perfectly compatible with each other. So we're not gonna make any huge improvement on the relative motion framework from the Central Atlantic, but we can make adjustments to the Equatorial Atlantic. And you can see here, I've plotted about 6 former reconstructions from the literature. Bullard's was the loosest. And then in my thesis in 1985, I proposed a tighter reconstruction. Others have adjusted that further in time, one of whom was myself in 2006 with Lorcan and Kennan. But for the first time in my life anyway, I finally had a way to check up on this using ION data. And we spent a week or 2 at ION trying to figure out which of these various reconstructions might be most satisfactory. And we don't think any of them was perfect. We could find problems with all of them, but in general, some of the tighter ones over here were the better ones, and the ones that were looser over here are the better ones. So I'm just using the coastlines to compare these different fits, but obviously we're most concerned with the amount of continental crust in the offshore underneath the continental shelves of both of these 2 continents. Anyway, when we use this heavier black line, you can see that it is tight over here and looser over here. And the difference with the older reconstructions gets greater as you head to the west. It's slightly canted even here, but when you project this over to the west, it makes quite a difference. So relative to the original vector that I used to use in black, the revised position for South America through time would be in the blue. And it's about a 200 kilometer difference. And that turns out to be enough to make room for Yucatan between South America and North America at 168. So 167 is down here, 168 is way up here. And that 200 kilometers, 220 kilometer difference is sufficient for Yucatan to fit in there. Now, this also has implications for onshore Mexico. We used to think that quite a lot of Mexico was overlapped by Colombia. Now we have 200 kilometers less overlapped with Colombia. And on top of that, we have to think about the reconstruction of the Andes. And we can do things like this to the Andes. First of all, we want to pull off all the Cretaceous arcs and so forth. And then we need to try to restore some of the Cenozoic offsets on strike slip systems like the ones through the Merida and the Santa Marta Fault, Bucaramanga, and other faults down and through here. We think we can make a better depiction for South America prior to the Oligocene doing these things, and other things could have happened in the Laramide, and we don't know that yet. People are still working on these things, but this is a safe, it's a conservative restoration for the Andes. And when we plot that onto the new position for 195, full closure, that is the outline of the Andes. So rather than, we've now opened up quite a lot of central Mexico so that it's not overlapped by Colombia. And it's even possible that more of that the Andes could be retracted further to the south. We don't know for sure. But this is getting to the point where between that correction and the realization of the Arperos suture, there is not that much of peninsular Mexico. I'll call this peninsular Mexico, Eastern continental Mexico, that is actually overlapped by Colombia. We have just the southern central bit of Eastern Mexico, and then the Oaxaca Mixteca block down and through here. So I want to talk now about another mechanism. Most of the people I worked with at UNAM are not impressed with the Mojave Sonora Megashare. I think that's an understatement. So in the program, I was always looking for ways to try to avoid that. Can we understand the regional geology doing something different? And that's what I want to propose to you. And I will be the first to call it nothing more than a proposal. We wanted to look into the possibility that this area arrived here by broad transtension, slightly sinistral, but extensional deformation along northwest southeast trending faults, as we saw on the introductory map. It's possible that if we have enough extension coming all the way down from up there, we might be able to get this crust far enough south. Once we get to Quicateco in yellow, then Oaxaca what I'll call the Oaxaca block down here, seems to be pretty much intact, and there's not too much more deformation taking place. Maria Sierra has done a nice paper recently on some smaller rifts in through here, but they're nothing like the scale of what I'll show you for Quiqueteco. So let's move and look into Quiqueteco a little bit more. I'm going to call that heavy black line the North Oaxaca transfer. And I'm going to tell you right now that this is a possible site of dislocation between the continental crust of what I'm calling peninsular Mexico and Oaxaca, Mexico. So we'll see where that goes. This is a map from Rod Graham's paper that was published last year in the GSL London. Some things to point out. Here's Quiqueteco in general. We have the Via Alta fault, which is a left lateral high angle myelinitic fault zone. Roberto and Rod and I found this a couple of years ago, and Juliana Estrada looked at thin sections for us, and she determined that that was left lateral shear. And then we come over to the Juarez myelinite over through here, which Alanis has worked on with others. And this set of myelinites and that set of myelinites we think must be related, because the laramide deformation in through here is not strong enough to cause myelinites to come up to the surface. We don't think from 10 kilometers depth. We think these things must be older than that. So we spent a lot of effort trying to provide better dating on the Juarez. We don't have any ages on the fabric of Via Alta. We just know its structural facies. So that's all I'll say at this point. Here's some of the results of the dating. What we were able to determine is that you can see Alanis's dates here somewhere, 178. I think she had a 158. We also got a 158. But we were able to get crystallization ages, uranium-lead crystallization ages on rocks that had been myelinitized as young as 132. So we think that the myelinitization probably started in the Jurassic, but it continued up to about 132. And we think it was an extensional type of deformation, which led to this, because Diego Villagomez has cooling ages on muscovite of about 130. So it's a rapid cooling situation, rocks coming to the surface quite quickly. And I made this cartoon this morning just to help try to explain what is a very complicated situation. I would direct you to Rod Graham's paper if you want to read more about this. But the main news is this: there's a foliation in the myelinites. The strike's about 160, which is slightly east of south. It dips 30 to 40 degrees to the west. And there's a strong stretching lineation along the entire belt with an azimuth that ranges from 170 to 190, and the plunge dips. It's sub-horizontal, but it dips south a little bit for the most part, but it undulates along strike. And maybe that undulation is due to the younger laramide deformation. We don't know. But just imagine taking a block and then chopping off a corner like that and letting the block move to the south in the direction of the stretching lineations, and the plane of motion is the foliation that strikes to the west, that dips to the west, 30 or 40 degrees. So this blue shape here originated up where it's gray, and that's this piece over here. So the bulk strain seems to us to be one of trying to move to the south, but there's an extensional component as well. And so that's what it is. It amounts to sinistral transtension. And it's at a very large scale, because given that these rocks were forming right up to 132, that brings us up into the time when the Jaltepetango and the Chavillas formation were starting to get developed, and starting to get deposited. So now we have a tie between structural geology in the basement and the onset of sedimentation in a basin that fits the structural geology very well. So we think these two events are tied together. We have a transtensional deformation that then and that leads to accommodation space that becomes filled with those two formations. So we interpret the strain as evidence of sinistral transtension. Mind you, we're talking about 10 to 12 kilometers depth, because we're looking at myelinites. So that means we probably had extensional basins at the surface well above. Further, the myelinization affects rocks as young as 132, and it's already cooling by 130. Taken together with the ages from Alanese Alvarez, we consider that the transtension occurred from middle and late Jurassic right through to about Valanginian, early Cretaceous. The accommodation space created by the transtension was filled with Haltopatongo and Chavías formations. And the pillar basalts in the lower Chavías, we interpret them to indicate very strong crustal attenuation. And the strain cannot be dextral, or else it would have produced crustal thickening, given the structural data, instead of thinning. Juliana Estrada has shown that the myelinites on the Via Alta, which we think is related, are sinistral, not dextral, from studying thin sections. Okay, so now we can go to the cross sections that Rod Graham has made. And this is just one of 3 or 4, but it's the present day sort of simplified cross section. We have the basement of Oaxaca block coming up. There's the Oaxaca fault. It has been, the Oaxaca block has been down dropped relative to the eastern side. And he hypothesizes that the Oaxaca block used to be way up here. It's been dropped down. And then we have all these sets of folds and thrusts across the top of Quicoteco and then down into the Western Veracruz fold belt and the Sierra de Zongolica. When he restores all this, the depot center for the Chavías deep water section ends up completely to the west of the Quicoteco belt, because the extension is something greater than 70 kilometers, greater than 50 kilometers. Anyway, the depositional site for Chavías is no longer on top, and it ends up sitting between Oaxaca and the Chavías basement. And if the crust was thin enough, we would expect it to do 2 things. It might start to get intruded with igneous material, which is what Chavías formation does, and it might be a deep water depositional environment, which is what Haltopatongo and Chavías formations are. So in addition, we have this strike slip deformation that we just talked about. Remember, the net strain between these 2 halves has to be directed toward the south. So there's a strong strike slip deformation in addition to this extension. So that amounts to transtension. And it may be that a lot of this is pure extension, and there are coexisting pure strike slip faults, such as the Via Alta, and that would lead to a kind of strain partitioning. But we don't know enough to start to think about that in that direction yet. But this leads, and then there's the cartoon. This would be the restored situation where the Chavías Basin sits between Oaxaca and the Quicoteco basement over here. The Cordoba or Azaba platform sits on the Quicoteco, and eventually that will get imbricated into the fold thrust belt during mainly laramide shortening. These would be the hypothetical positions of where these thrusts would root into the basement and bring these rocks up. So this would be a laramide depiction of what's going on. And then subsequent to that, from Oligocene onwards, we have the big normal faults cutting through the system and allowing the Oaxaca block to drop back down to the west relative to the structural elevation of Quicoteco. So it's a pretty radical change in the view of what the Quicoteco belt is. And if we tried to draw this in map view, here's the present day. And we can trace this right up to the edge of the volcanic belt. And then unfortunately, it goes under the Trans-Mexican volcanic belt. So we cannot try to test this any further in that direction. But if it is a strike slip system, we would infer that that would have to go far enough to the northwest to hook into the Arperos Seaway prior to that becoming a suture. So it gives us the possibility now that all of Oaxaca, and if we wanted to attach Chortis, the Paleozoic core of Chortis block to Oaxaca, we could do that. In fact, there may be a basin exactly the same age sitting between these 2 blocks. I don't know. That was, I think, Peña Alonso proposed that. But here's our East Mexico transform. Here's the Quicoteco in yellow. This would be the big detachment. And then the Haltopatongo Chavías Basin would sit between Oaxaca and the Chavías, or the Quicoteco basement, the CB. Okay. And the Via Alta is this fault right in through here, which we know was a high angle strike slip fault. So this one could be transtensional, this one could be true strike slip, and between them, we might have a situation of strain partitioning. But the basin, the accommodation space that's formed by the transtension lies to the west of Quequeteco. And then when it all starts to close down in the laramide, then all of that gets scooped up and pushed back up onto the Quequeteco basement. Okay, well, using that kind of a model, that theory, that hypothesis, we could take what we have inferred from field work along the North Oaxaca transfer, and we might entertain a similar type of history on all these other faults up through here. We haven't done the field work on these faults to test this. Hopefully others would be interested enough to try to do that. The Huayacocotla might be a good place to start since the old section is exposed. But we think, again, all these northwest-southeast trending faults between basement blocks, including Huayacocotla, the North Oaxaca transfer, and the en echelon faults through Tamaulipas Arch, as well as the bounding faults of Coahuila and a couple of other possible linears over here beneath the thrust belt. We think all of these could be acting in an en echelon extensional kind of way. We know when the rocks were intruded that form the basement of a lot of these blocks. Henry Coombs's thesis did a very nice job, and we worked very closely with Uwe, and they've determined all of these new UPB ages on the basement blocks in through here. A lot of these are anatectic. So let me just run through some of these details. They're mainly northwest trending basement faults in the pre-Mesozoic crust. Babia, San Marcos, Tamaulipas Arch, en echelon faults across Tamaulipas Arch, Huayacocotla, Tuxpan, Valle Nacional, Vista Hermosa, North Oaxaca transfer. Okay, so there's a good number of those that you can point to, and these tend to be the biggest faults in the system, so we're impressed with them. Above this whole area, we have 3 to 8 kilometers of Mesozoic sedimentary section. So that's interesting. And then red beds, salt, or the first marine onlap rests on these basement rocks. So these rocks have to be exhumed to the depositional surface before Triassic red bed deposition or Jurassic salt deposition. Okay, so this is a longer history of extension than I think most people have entertained. And in order to do that, you got to get these rocks from maybe 10 kilometers depth. You got to get them up to the surface before there's any sedimentation. And the sedimentation ends up burying those exhumed rocks. So that sort of indicates that the whole topography must have been well above sea level, maybe 2 or 3 kilometers elevation at the start of this extension. And then the red beds only start to get accumulated once there's been a lot of extension and these rocks are already exhumed at the surface. And not only that, we end up putting 3 to 8 kilometers of Mesozoic section up on top of that crust. Well, that tells us that the extension went past the normal 30 kilometers thickness for continent, and it went something less, perhaps 25, 26, 27, something like that. And that kind of a crustal thickness would allow the long-term accumulation of 3 to 8 kilometers of section on top of it. So this all implies a very strong crustal thinning before the onset of sedimentation, and that crustal thinning went past the normal thickness of continental crust of 31 and continued to about 27 or 26. And that will give us the accommodation space for the Cretaceous carbonates and everything else we know about for the Cenozoic. So a possible model here, like this is dumb, stupid, silly, simple, but you know, it's the concept. There are much more fancy diagrams from various papers that you could use, but we know we end up with about 25, 26, 27 kilometers thickness, and we know that some of these mid-crustal intrusions end up at the surface in order to be the basement surface that the red beds are deposited on. So to shove that back up to the thickness that you might expect, turns out to be about 50 kilometers. Maybe this crust started extension when it was 50 kilometers. Why do I say 50 kilometers? Well, in order for the southern part of peninsular Mexico to avoid overlap with Colombia, we need to cut the area of the blue dashed line by about 50%. So that would require a crustal thickening of 100%. So we push back the 25 kilometer thickness and we go all the way to 50 kilometer thickness. And that would let all the crust that occurs in the area of the blue dashed line fit into the area of the pink. All right. So this is the new mechanism for avoiding overlap with Columbia, and we are not using Mojave Sonora at all. In addition to that, we know that the Chiapas Massif, which is part of Yucatan, sat right here at the end of rifting and the onset of drifting. This would show where Chiapas Massif is if I had plotted Yucatan here at about 165 million years, okay? We know also that it has received anatectic intrusions too, and that the red beds sit on some of those. So it has also gone through this extensional episode. So it needs to be shrunk some amount, and I can shrink it about the right amount, and we can stick it back into this position here. And now we have this pink shape for the mid-Triassic outline of thick crust, which is going to start to fall apart as we begin to separate North America and South America. And what I did here, I took an outline of the magnetic map of Chiapas Massif, and I have rotated this about 40 degrees so that it would be in the right orientation that we think Yucatan was at the onset of spreading. And you can see that the crustal fabric of the Chiapas Massif is exactly parallel to the northwest, southeast sets of faults that we want to restore in the onshore part of Mexico. So it looks to us like maybe this fabric applies to all this crust, but we can't see it because of the overlying section plus the laramide deformation. That's a hypothesis. But this new stretching mechanism would allow us to get this, and all it takes is a 50 kilometer thick crust, which is thick enough for you to expect anatexis in the first place. And then we've got to extend that to the point where those intrusions can come to surface. So we're talking about huge extensions anyway. These are ballpark numbers. They can probably be refined. It would be interesting to get into pressure, temperature, and the timing of uplift of some of these rocks. Okay, and just one final note. We think that the extension that we're talking about continued right up into the Oxfordian and even into the Kimmeridgian. And according to Horbury, possibly even into the Tithonian. So the faulting that some of these faults, locally anyway, may have continued into the late Jurassic. Okay, and the orientations of these are again, generally northwest, southeast. Okay, finally, before we get to the evolution maps, I just want to do a quick little explanation of what all these horse and grobens in Florida are about. It's a very curious thing. If we just work with that hypothesis, a groben, a horst, a groben, a horst, a groben, a horst, we know that the Sin Rift extension direction was northwest, southeast. Okay. The surface that map is mapping is this one. That's the top Rift Unconformity. This is just a line somewhere in Florida. Doesn't matter where. And we have Alleghanian deformation beneath it, and then the Jurassic section and younger above. So that's what this is. And that you can see that. So wherever there's a big basin, you would get thermal subsidence after rifting. And that's what we're actually seeing here, just the thermal subsidence. We're not even looking at the Sin Rift extension between these horse. Anyway, you can see, just let's use our stuffing the extension back into an original brick of 31 kilometer thick crust. If we draw the cross section along here, this is what it looks like. Okay, these are the basement depths. These are not the basement depths. These are the unconformity depths. So in order to, and then from that, we can use different densities to predict where the moho should be in order for this to be isostatically balanced. And then from that, we can start to shorten the brick back into an unstretched piece of crust. And it turns, depending on what density you want to assign the carbonates, whether it's 2.5 or 2.7 maybe, you can come up with extension values of 300 to 400 kilometers. So there's a lot of extension taking place there. And it's a very strong argument for the existence of a Florida transfer zone. On the other side, we don't see any evidence for that whatsoever. It's just a southeast trending peninsula. So there may be some sort of a transfer zone in through here. And if I had to guess, I would think it dips to the west, and it's not a high angle structure. It's a low angle detachment. And these things are just breaking above the mid-crustal detachment. Okay, I'll just finish by running through these evolutionary maps. This is the full closure. The Andes are restored in all of these. The early maps have the extension in Florida restored that I just showed you, and there's the Florida transfer fault. Peninsular Mexico has been shortened by 100% to make a very thick crustal root in this area, maybe 50-kilometer crustal thickness. That would give about 2.5 kilometers elevation prior to extension. And then here's our North Oaxaca transfer. And because that transfer allows us to dislocate Oaxaca from the rest of Mexico, we can push Oaxaca back to the west as far as we need to avoid overlap with Colombia. And these maps indicate that it must be somewhere over there. So that there's going to be, well, I think it was 300 or 400 kilometers of net sinistral strain along that zone, which might be represented through Quicateco. Okay. What else is on here? Here's the magnetic anomaly along Campeche, sitting right on top of Houston magnetic anomaly, same trend, very similar looking anomalies. And now we're going to start to separate North America and South America. And as we do that, you can see that Yucatan sits between the North Oaxaca transfer and the Florida transfer. And it may be that Yucatan is rotating as a lozenge between these two transfers. This was an idea published way back in 1994 by Hans Schouten and Kim Klitgård. And after 26 years, it looks like that idea might need to be reconsidered. Okay, this is 177 million years, Middle Jurassic now. We're putting down red beds everywhere, and you can see quite a lot of extension taking place along peninsular Mexico. You can also see that Oaxaca block is moving down along North Oaxaca transform. And basically what's really interesting is that that structure ties in perfectly with the offset in the Andes. Okay, we would call that the Falcon marginal reentrant, marginal offset, and that seems to be directly on trend with the North Oaxaca fault. That's kind of neat. Okay, then we can go to 167. This is now the reconstruction where Yucatan is far enough away from North America to hold all of the autochthonous salt. So that could be the time of salt deposition, 169, 168, 167. Okay, by this time, we think Florida has extended completely because that unconformity I showed you is never faulted. And when the Jurassic onlaps that surface, it simply onlaps that surface and it doesn't get faulted. So the extension over here is probably finished by this time. This extension is critical for companies working along Guyana and Suriname because it keeps the Great Bank crust of the Bahamas in contact with Demerara and the Guinea margin until the edge of this map. And then going forward, that's going to start to separate. But if you don't account for this extension, you end up predicting a much earlier separation between these two conjugates here. And so far, the geology favors this kind of a separation. The only dredge of igneous material of the hotspot responsible for Demerara has a 173 Argon age, which is close to the age of this map. So it looks like that hotspot is active and it's going to form the southeastern Bahamas as we continue to separate. Okay, so Yucatan is now going to start to rotate about this second pole of rotation in through here. That's going to be the first orientation of seafloor spreading, and it's going to start the East Mexico transform. These blocks will continue to extend and Oaxaca will continue to migrate to the southeast. So this is all much, much larger. And as this tenses, if that's a word, undergoes transtension, the trace of the North Oaxaca Fault also migrates to the south. At some point, Mexico and the Andes will stop being in contact. And we think this is about when we start to have seafloor spreading. We've got seafloor spreading going in the Gulf of Mexico now. The extension here is almost finished, and the insertion of Oaxaca block is almost finished. We go one more step to the 154. Now we have this much oceanic crust. East Mexico Transform Fault is still forming, and somehow it ties into the spreading system here. Oaxaca block can be in place at this point. Okay, and then this goes transtensional, and we form the Jaltopatongo-Chavías Basin after about 147. And we also, in the Gulf of Mexico itself, we have the change in the orientation of the spreading. And now we're forming the new crust around this younger pole, which is where the gravity image of the ridge points. So there's been a reorganization of the crustal fabric in the middle of the GOM. The extension is now finished in the onshore. Mexico is now basically dead until the Laramide. And then one more step, finally, Yucatan is able to reach its final position. So that's the final step in seafloor spreading. And that is also around pole 3, which now becomes extinct in the Valanginian. Okay, so now how do we know that that's when spreading stops in the Gulf? The best estimate still comes from Georgie Martin's thesis in the early 90s. The extension between Florida and Yucatan ended at the end of the Berriasian and just going into the Valanginian. This basement extension probably pertained to these faults right here, just northwest of the polar rotation. Okay. When that extension stops, I think we can say that Yucatan stopped rotating. And that was one of the big points of his thesis. I still think that's accurate. And then any further motion after 137, going to 121, all of that takes place in the Proto-Caribbean, and the Gulf of Mexico became dead. So the hotspot, which grew off the edge of this continental crust, forms a hotspot trail in the eastern Bahamas. The Proto-Caribbean Seaway is now forming, and it's bigger by this time than the Gulf of Mexico. But still, all of these are passive margins. And certainly by this time, all of the Caribbean arcs are starting to form. And you can't be forming the arcs in the same area as the passive margins. And we don't see any changes to these passive margins till the Maastrichtian. So the arcs have to be somewhere off into the Pacific. So Pacific origin for the Caribbean crust. But when it comes to the Gulf of Mexico, that's the synthesis that we've been able to do, trying to merge everything from the onshore that we've studied in the Cordilleran program with the offshore that I've been able to do with ION. Okay, so some final thoughts. Integration of plate tectonic field and lab scale work continues to be essential to understanding regional evolution and analysis. This revised evolutionary model provides new ideas for testing at finer scales of work. For example, does the Cuicateco belt represent a Jurassic early Cretaceous zone of mid-crustal sinistral shear with strain partitioning on high angle and low angle shear zones, together recording crustal transtension and overlying rifting up at the surface? Also, how well does a regional extension model for peninsular Mexico fit the actual basement geology? We mentioned Anatexis. We talked about mid-crustal unroofing on moderately dipping sinistral northwest-southeast trending faults and shear zones. All of that has to happen prior to the deposition of the red beds, or the red beds come in late in that history. And the crustal thinning to about 25 kilometers. There's a lot of sort of secondary evidence that points to this larger model, but a lot more could be done to constrain these in more detail. So do they stand up? Do these things stand up to more critical examination? Or do we need to return to the Mojave Sonora Megashear. All right, that's it. I'll thank you for listening. I want to thank Roberto and Uwe for inviting me to speak. I want to thank all my colleagues for collaboration over the last 10 years working in Mexico. And thanks also to UNAM for collaborating in the program. And I guess I'm happy to take questions. Thank you very much.
Hi, Jim. Thank you. It was a great talk, and I'm sure there will be questions. Por favor, todos los que tengan preguntas, les recuerdo que las pueden hacer a través del chat, que está abierto, y las preguntas que hagan yo se las voy a leer a Jim. Entonces, si alguien tiene preguntas y quiere compartirlas.
I'm going to need a translator.
That would be my job, Jim.
For Spanish questions. I'm sorry. I promised Luca I would learn Spanish, but I think I was too old.
Hola por ahí. Nadie se anima a preguntar. Ok. Rodrigo, ¿quieres anotar la pregunta? Rodrigo Portillo, anota la pregunta y yo la traduzco para Jim. Lo mismo después de Rodrigo Alejandro.
Sí, buenos días. ¿Me escuchan?
Sí, adelante.
Mejor rápido, creo que voy a tardar más en escribirla. Ok, gracias. Antes que nada, felicitar por la invitación, y por la gran charla al doctor Pindell. Yo tengo dos preguntas. Una, en las primeras etapas de apertura del Golfo, obviamente tenemos el Rift del Golfo de México, y hacia la parte sur, pues otro Rift que viene siendo la separación de Sudamérica con el bloque de Yucatán, ¿no? Entonces, mi pregunta número uno es, ¿dónde se acomoda toda ese acortamiento, toda esa extensión que se da por la apertura del Golfo, que no veo en la parte sur de Yucatán o Chiapas? No veo unas fallas inversas o plegamiento. Sin embargo, tenemos otra zona de extensión, otro rift en esa zona que está separando Sudamérica. No sé si han visto algunas evidencias de esa extensión que yo estoy teniendo en una parte en el Golfo, y ese acortamiento que podría, como respuesta a esa extensión que podríamos tener en el bloque de Yucatán, ¿no? Esa es una pregunta.
Okay. So Jim, he thanks you for your talk, but he is asking about the extensional basins that existed between Yucatan and South America.
Okay.
Now, during this the rift stage, the Sin Rift stage of opening of the Gulf of Mexico, what is happening in the between Yucatan and South America?
Okay. A lot is similar with the Gulf of Mexico. However, the rifted margin there has no Triassic. It looks like all the red beds which have been dated are Middle Jurassic. So one way of interpreting that is that Yucatan first pulled away with South America, and then the extension between Yucatan and South America is a little bit younger. That margin, those margins, starting, we have it in Cuba, Western Cuba, we see the Proto-Caribbean passive margin. And we have the Caracas group in central Venezuela and Northern Range in Trinidad and Araya Paria peninsulas in Venezuela. All of those are late Jurassic deep water marine sections. So we know that those basins between Yucatan and Venezuela were already marine by late Jurassic, but the red beds have igneous material in them of about 162 million years. And I think there's early and middle Jurassic indications of rifting as well. So the rifting started a little bit younger, possibly because it wasn't an orogenic root that was collapsing, such as we might have had in northeastern Mexico. But that basin, just like the Gulf of Mexico, went marine by late Jurassic. And that's about all we know, because the Caribbean has pushed those sections out of the water and we can study those. But the crust that was actually formed between Yucatan and Venezuela has all been subducted. So there's not very much to look at. Just those sections in those places which have been thrust out of the water by the eastward motion of the Caribbean.
You don't think, Jim, that the process that stretched what you call peninsular Mexico acted the same way in the Andean?
Okay. I hope he was asking about the eastern part. But if he's talking about the Andes, yes, there is also extension in the Andes. Quantifying that is very difficult because of what has happened in the Neogene in the Andes. But Richard Spikings and his students who have been working in Colombia for about 15 years now, they have a very similar story, and they have anatexis and they have extension and red beds being put down in extensional basins between basement highs. So yes, I see what you mean. That story seems to continue across into Colombia. However, as far as we can tell, the trends of the bounding faults controlling the process are almost at right angles, except for Bucaramanga, Santa Marta. If I went back to the if I went back to a Sin-Rift stage, Bucaramanga, I don't know, it might be down in through here. So it doesn't seem to be related very much. So I don't know. The faults have different trends. The same processes might be going on, but it's not the same terrain. There's something fundamental between them. And these reconstructions suggest that it's the North Oaxaca transfer and the Falcon reentrant.
And of course, there's no record of rifting south of, like in Chiapas or Yucatan, because that's overprinted by Caribbean tectonics, Rodrigo.
Right. Okay. Well, as you know better than anybody, the Todos Santos south of Chiapas is thrusted to the north, and that was probably an Oligocene event. So there is a red bed section on the south side of Chiapas, but it's all cleaved and folded and thrusted now. And we have no idea what that margin once looked like. And there's nothing left on the south side of Guatemala, as Uwe knows.
Okay, so I'll go with the rest of the questions. Okay. Rodrigo Alejandro asked if your North Oaxaca transform is the continuation, or is the continuation of the Oaxaca Mylonite belt? And I think you would say yes.
I think I would say yes, but remember, we could be talking about multiple faults. So it's a fault zone. The Oaxaca, the Juarez Mylonites looks to us to be a low angle detachment. So it would be transtension in order for the stretching lineations to be southward. But the Via Alta was a very high angle foliation. So there could be both types of faults operating together. So you have strain partitioning. I want to say one thing that I didn't say before. this model for the Juarez Mylonite does not require any strong rotation in the foliation in order to understand how it got to be the way it is. I think in the original Alanese model, the assumption was that the foliation would be high angle because they thought it was a strike slip fault. And then it would have to rotate top forward or eastwards by about 50 degrees on a regional scale in order for it to come up with its 30 to 40 degree westward dip. And that posed a problem for Rod and I because the foliation is so consistent from north to south along the whole belt. So this interpretation doesn't require the rotation. It's just, it is what it is. It's been uplifted again in the laramide, but it hasn't needed to be rotated. It might have been rotated some, but we wouldn't know.
Okay. I have a question from Jorge Arzate. He wants to know what kind of magnetic anomalies are you looking at in these interpretations? Are you looking at total field, some residual anomaly, or some other
In the
process?
offshore?
In the offshore, in the Gulf of Mexico.
That is a total magnetic anomaly reduced to pole
Okay.
presentation, and it's something that Pemex had shot for them back in 2003. They were processing it from 2004, 5, 6, and I started working with them on that map in 2006 and 7. And it was pretty clear that it recorded that rotational seafloor spreading. Now that was all prior to the gravity maps being able to see the ridge, where the ridge died. However, by 2006, the satellite gravity was good enough to see the death of the ridge. And we knew, in fact, G-Tech made the first map I ever saw, which shows the dead ridge. And that map is on the cover of the 2009 GeoSoc London book, representing the first Siguenza meeting that Keith James organized in Spain. So anybody can go and get that early map, and it's a color version of the Sandwell map, and you can see the ridge just as well. Yeah, anyway, reduced to pole, full magnetic anomaly.
Thank you, Jim. There's a question from Marta Marin. She's interested in seismicity in the shelf and continental slope west of Tamaulipas and Veracruz. I know that this seismicity is probably new to tectonics, but I don't know if you would like to comment on that.
Let me see. I'm not very much aware of the seismicity, but I was certainly aware of the big shock that happened a couple of years ago, and I know that they do happen. Those ones would be due to subduction, presumably, but there's also some great elevations of the crust of that northeastern portion of Mexico, and perhaps she's talking about those. I think Gary Gray's work showed significant uplift of basement rocks since the Miocene, kilometers of exhumation since Miocene. Most of his uplift was since the laramide, but I think if you interpret, you can look at his AFT plots, hefty plots in particular, and you can see that there's continued uplift after the Miocene. So yeah, just what is that about? I don't know. It could have something to do with the detachment of the Farallon slab. It could be something to do with mantle coming into the slab gap, which occurs along the Gulf of California. I don't know. I don't think I can answer that question very well. That's not the kinds of things I looked at, and I'm just babbling. I think other people could do a much better job than I.
That's all right. Perhaps someone would like to comment to Marta in the chat if they want to help her with that question.
Okay.
There's a question, another question from Rodrigo Alejandro, which is asking if that change from 50 to 25 kilometers through extension that you propose, he's asking if that is generated as, you know, how do you reach that? I mean, what is the process that allows you to extend across that much over that long of a period of time?
Okay. Well, as you, Roberto, have shown, North America is the plate that departed from the central core of Gondwana. And you can find most reconstructions show North America migrates northwest away from Gondwana. And it crosses paleolatitude, and eventually it ends up in a place where you might expect evaporite deposition. But back in the Triassic, it was in the doldrums on the equator. So it takes off to the northwest. And I don't know if there's any age migration in the locus of the faulting, but let's just entertain it. Let's say that that central knot of thick crust starts to, I mean, you could call it post-orogenic collapse, probably. And the exhumation of the mid-crustal plutons would be due to that process. So it could be a widespread event that is happening, but it's the departure of North America which makes room for that to happen between Colombia and, say, Arizona. You can't start the process until North America starts to depart. And we think that's in about, you know, latest Triassic. There might be the initiation of extension taking place. So that can start to fall apart, and these rocks can find themselves coming to the surface. That fabric, that northwest-southeast fabric, might have been a Paleozoic fabric that was reactivated. I don't know. And there may be some southward younging in the locus of rifting. That seems to be a possibility, because the Quiqueteco and the Haltopatongo Chavillas might be the youngest big basin we know about. So North America moves to the northwest, and maybe things stretch out, and there may be a growth of the area that was stretched, migrating from northwest to southeast. Those are the kinds of things that need more careful assessment from people who know a lot more about the basement than I do.
Okay, thank you, Jim. Yeah, I think that's a good hypothesis. Is that the motion of North America to the north is fast and is in the Jurassic, and that might be leading to stretching in the southern, the trailing edge of that plate. We have a question from Alex Iriondo. This one is in English. I'll just read it to you. He thanks you again, and then the question is: do you think there is subduction going on west of your Permo-Triassic and Atlantic belt in northeast Mexico? And if yes, where is the continental arc for that time with respect to the Antarctic belt?
Okay. Well, perhaps the arc is helping to contribute to the Anatexis. I don't know the answer to the question, and I know why he's asking it. It's a very obvious question to ask. I think the NASA starts to become active in the 190s, and we don't have a lot of extension that can take place prior to about 210, maybe, because of the relative motions involved, maybe 220. So there's a, the onset of the extension does not predate the NASA's arc by very much time. So it may just be that the extension yeah, there probably is a subduction zone under Mexico during the extension, and that becomes Nazas. And I remember Busby talks about the transtensional arc of Nazas, and she shows that it sits low because of the extension around it. Now, backing up to the late Permian, earliest Triassic, is there eastward subduction? That's a very good question. I know there are papers that have interpreted one, but I'm not sure we appreciated the full extent of the Anatexis until Henry Coombs's thesis. Maybe Uwe could comment more about that, but whether you could find a trend of a Permo early Triassic arc that is separate from these plutons, I don't know the answer to that. If they exist, there's a very good chance they're covered by the fold belt, or maybe even never made it to the surface. I know there is a paucity of volcanic detritus of that age. So wouldn't surprise me, perhaps, that there isn't very much subduction going on.
In the Permian or in the Triassic?
Late Permian and into the earliest Triassic.
Okay, because I think Alex is coming from the idea that in Sonora they have dated early Permian granites, and they think that's subduction.
Early Permian, right?
Yes, and he's also aware of the Delicias arc of the Maquis in Coahuila. You know, the idea that there are at least volcanic rocks of Permian age in the Delicias arc. Okay.
Right.
So
yeah, well, I guess the question is whether those are related to the final closure of Gondwana or the Pacific arc outside of it. And that's something that Henry got into, and he toyed with the idea of some of that being anatectic, but not all. So maybe it's both.
okay. I think there's one more question. Alex, thanks you for your.
Thanks, Alex. Hello.
And I'm going to take this last question because it's late. And this one is from Rodrigo Portillo. It says, did you expect to see a difference in the Rift deposits along the transform, the West Gulf transfer, like Burgos and Tampico, compared to within the Gulf of Mexico itself? It's a difficult question because we don't know what the Rift looks within the Gulf. And I don't think,
okay.
Yeah, you go ahead. Maybe you have seen it in there.
There, Bob Ehrlich is working. There's quite a lot of red beds in South Texas that have been drilled, and it's called the Eagle Mills. And a surprising amount is known about it. And people are starting to do detrital zircon studies on it. So far, I hope I don't pre-speak what this person is working on, but a lot of the detrital zircons on the North American side have Pan-African and sort of carboniferous zircons in them, very much like we're seeing in the red beds of Campeche. So I think suffice it to say, you can make a decent case that a lot of that material is south derived, and that Yucatan may have been a very high block as it detached off of the North American footwall that defines the Gulf of Mexico. And it may be that, what I've always called the Burgos transfer zone, that might be a fundamental break in the crust where the polarity of rifting is Yucatan coming off of Texas to the east, and then a completely different structural style to the west. of the Burgos lineament. And what I mean by Burgos lineament, if you don't know that, there is a striking magnetic anomaly on the eastern side of Tamaulipas Arch, which you could see from outer space. And the Tamaulipas Arch is west of it. So it's the anomaly is where the basement surface dives down into the South Texas Basin and the northeastern part of Burgos. Something changes very, very much there. I used to think that was a zone of strike slip motion, but in this new model, and I probably should have said this new model does not require that to be a strike slip fault. It can just be a fault surface. It can be a detachment, and it might be a lateral detachment where Yucatan came away from the eastern side of Tamaulipas Arch.
Thank you, Jim. I don't think we have any more questions.
Okay.
Maybe Lucia, did you?
Hello, Lucia.
Your camera.
Hi, Jay.
How are you?
Thank you for your talk. Just to say hi. Nice to meet you.
I am happy to see you, and
again.
I'm very grateful for what you've made possible.
Yeah. So are you planning to visit Mexico soon?
Well, it's not up to me, is it? I would love to come, but I think Mexico is still, I still have to sit through lockdown when I come home and everything. I would love to come.
Okay.
Maybe 2022.
Okay,
We'll
will
see what
be
happens.
Welcome.
Well, that's very kind. Thank you. Thank you. I would like to see all you guys.
Thank you. Thanks for your talk.
You're
We
welcome.
did a lot of work with Roberto
All right.
and
Great.
other people. Thanks again.
Bueno, pues gracias a
Okay.
todos los
Thank you,
demás que
everybody.
estuvieron aquí. Terminamos la plática. Thank you, Jim.
All right. Time